20 minutes for questions. Okay. So Marco will talk about upper bounds for Pythagoras number of fields.
Okay, so I would like to thank Adam for the introduction and for inviting me to Tel Aviv and to give a talk. So I gave a talk about a year ago about with a very similar title. So some of you were present and asked me if it's the same, but no, it's not the same, and it will actually be somewhat complementary to that talk, in the sense that in that talk I described how to compute upper bounds for Pythagoras numbers of certain fields by applying a local global principle, which has complicated and deep proof. Whereas now I would like to show some techniques that somehow allow us to use simpler local global principles. So it's kind of complementary. And so I will anyway need to give the same definitions of last time, namely the Pythagoras number. So I will need a notation for the sums of n squares in a field, which I denote by S of n. So it will be something like this. I will need a notation for all the sums of squares in the fields. If I write too small, please remind me. And so the Pythagoras number is defined as the minimal integer such that n such that all the sums of squares in K are sums of n squares. Okay. So of course there is no reason why such an integer should exist a priori. So there are examples where this set is empty. In this case, we just set the Pythagoras number to be infinite. So let me remark immediately that for fields of characteristic 2, what happens? Well, we have the so-called freshman dream, which allows us to write any sum of squares as just a square. So the Pythagoras number is always 1, and the problem is there's nothing to work.
You mean
Characteristic equal to 2. Sorry. So I will work with fields of characteristic different from 2. Okay, also for some classic fields like the real numbers and the complex numbers, it's really trivial that all sums of squares can be written as squares. So the Pythagoras number would be 1. I think the most famous and basic classic example Pythagoras number that you probably know is that the Pythagoras number of Q is 4. We probably know the Lagrange's theorem, which actually says that all positive integers are sums of 4 squares of integers, but for Q it's a bit easy, and it was shown by Euler in 1752. Another famous result is somehow a generalization of this. So what happens if we consider a number field K? Well, then the Pythagoras number is at most 4. So this was proven by Siegel in 1921, but it's also known as Hilbert's theorem because Hilbert claimed this result. Let me give you another example, which might be a bit less famous, but it's very relevant for the talk. So if K is a finite extension of the rational function field in our real numbers, then the Pythagoras number of K is 2. Basically, it's function field in one variable over the reals. So this was proven by Witt in 1934. So, but in general, the definition of even though the definition of the Pythagoras number is very elementary, it's a complicated invariant compute. So we focus. Usually, people study either lower or upper bounds in separate ways. So we study in my thesis, PhD thesis, I studied mostly upper bounds. So this is a question that I would like to address in this talk. Good. So let me mention one more thing. So there is a class of fields, non-real fields, for which it's easier to find upper bounds. So the real fields are defined as the ones on with infinite level. So the level is smallest integer, such that -1 can be written as a sum of that many squares. Again, when it's not, when the set is empty, we just set the level to be infinite. So, as I was saying, when -1 is not a sum of squares, then the field K is called real, or sometimes formally real. And otherwise, K is called non-real.
Complex numbers are real.
Sorry?
So the complex numbers are real.
No, the complex numbers are non-real.
Why?
Because the -1 is a square.
Why can I take just one square?
So in the complex numbers, we have this equality.
Yes.
So -1 is a sum of one square.
If the value of sk is 1 or any natural number, then it's a normal. When it's infinite.
I got
Exactly.
the other way around.
No. So if -1 is not a sum of squares, then this set is empty.
Because you had two arrows and I didn't understand which was where.
Sorry.
So now I can understand.
Okay, so I was saying that for non-real fields, there is an easy way to find upper bounds. So the fact is that when -1 is a sum of squares, then of course the Pythagoras number is by definition bigger or equal than the level, but it's also at most the level +1. This follows from this annoyingly trivial identity. So you can see any element can be written as sub square plus -1 times a square. So if -1 is the sum of 3 squares, then any element will be a sum of 4 squares. And let me also mention that when the level is finite, then it is a power of 2. This was proven by Pfister in 1975. So it's not always easy to compute the level of a non-real field, but in general, there is a very natural upper bound for the Pythagoras number of the non-real fields. So, and you can also notice that the upper bound will be a power of 2 plus 1. We will be mostly interested in finding upper bounds for real fields. But, okay, let me conclude this introduction to the topic with some of the most relevant bounds present in the literature. Yeah, no, so the first 2 upper bounds the first 2 upper bounds concern number fields again. So K is a number field, and we consider a rational function field in one variable over K, and then there is an upper bound for the Pythagoras number, it's 5. So this was shown by Fouché in 1971. And already for such well-known fields, proving an upper bound is very difficult. So the Fouché's result is very technical and long. And, it's quite a complicated result. And if we consider a finite extension of such a field, then there is an upper bound which is 6. So essentially for transcendence degree field, transcendence degree 1 field extensions of Q, there is an upper bound which is 6, and it was proven by Paul in 1991. It's not open level principle by Cato, but it remains open whether there exists, whether actually one can improve upper bound. So not a single field of field extension of Q transcendence degree 1 is known where the Pythagoras number is 6. Yes?
Something like P of K plus 1 or with nothing?
Yes, actually it is. So
it's most P of K.
Sorry?
Like it most P of K plus 1.
It's not known for this field, but for in this case, so one has to separate if it's real, then it is indeed pk plus 1. If it's non-real, it's not possible to have it because if you take a field with a level with a Pythagoras number, so if you take a number field with level 2 and Pythagoras number 3, for example, then this upper bound here already forces us to. But it's true that the Pythagoras number of kx it would be the level of k plus 1. Or okay, so this are two important results. So actually, let me mention something that maybe didn't say. This is not published yet, but it should be published within weeks or months, according to Bob. But
Has it been published for 30 years?
yes, he left it unpublished for 30 years. I heard, but I don't have proof that he was hoping to achieve. Florian Bob. Okay, let me move to the next upper bound. So let's assume that there exists an integer, positive integer, such that I really need positive, so non-zero natural number, such that the Pythagoras number of any finite field extension of kx, so for any functional field in one variable or k, the Pythagoras number is bounded by 2 to the n. Then for any functional field in one variable over the formal power series over k, for any finite field extension of this field if you want, then the Pythagoras number is bounded by 2 to the n plus 1. So this was proven by Becker, supervisor, David Green, Johan Hill in 2014. And for example, let me show you a concrete example from discharge bound, which I erased before. One obtains that any function field in one variable over the real numbers, the formal power series over the real number is at most 3. So for any finite field extension of this field, the upper bound is equals 3. So this hypothesis follows directly from the bound that I gave as an example at the very beginning. And last one. So it's an upper bound by John Hu. So for any finite field extension of the formal power field of formal power series of 2 variables, the Pythagoras number is at most 3. This is a result by John Hu. So let me say these two results have quite different proofs, but they have one thing in common, one idea in common, which is, so I want to show that all sums of squares are sums of 5 squares here, for example. What does Fouché do? Well, he takes an arbitrary sum of squares and he subtracts a square, so that this difference will be a sum of 4 squares. So the idea is simple. You subtract a square in order that you can change properties of the. This difference will have different properties from the starting sum of squares, and you will be able to apply a global principle. And so the techniques that I'm going to explain now, they are inspired by this method, and I will try to show you how they somehow improve or simplify the proofs of these two arguments. There are also other applications that we give in our preprint, but I think to explain these methods, I can work with these two examples, with these two statements. So let's finally move to some real mathematics. Are there any questions before we begin? Sorry?
For the periodic numbers?
Yes, so the periodic numbers are non-real. So you just need to compute the level, and in order to compute the level, you can use so Semma. So one should deal separately with the dyadic numbers. So those have level and Pythagoras number equal to 4. For the other ones, it depends on so you have the periodic numbers where p is an prime integer, and depending whether the prime integer is congruent to 1 or 3 modulo 4, you will have a level equal to 1 or 2 in this order, I think. And the Pythagoras number will be S1 plus 1. And one can also deal with finite extensions of without too many difficulties.
And this multiplication is not commutative. Definitions make sense, but
I've never studied non-commutative. I don't know if, so there, of course, one can define everything for a ring, an arbitrary commutative ring. I know that there are people working on Pythagoras number of rings in general, and there is some literature also, but I'm not aware of people working with non-commutative stuff. Okay, so anyway, let's start with math. So last notation I give. So the techniques I'm going to describe now will be, I dare say, rather elementary. It's so I will just use algebra. Let's assume the characteristic is not 2. No, yes, okay. And for subring H of K, I need annotation for the Jacobson radical ideal. And we'll especially need the this characterization of the Jacobson radical ideal. So the elements of H such that Hx minus 1 are units H. It's a standard result. It's very easy. And I will need another invariant, which I denote by phi star. But this time it depends on the, it's a number depending on the subring, not on the field. And it is the smallest integer such that all units in H that are sums of squares in the field or sums of n squares. I see that I'm already moving to field F, so allow me to call it F, otherwise I'll make 20 typos. So again, for most strings, I guess, such an integer doesn't even exist. So in this case, we call it infinite. And so I will use this invariant to produce an upper bound. And let me mention, in concrete applications later, we will use H. H will be taken as a intersection of valuation rings of the field F. So this intersection of valuation rings are called holomorphic rings, so that's why I'm using the letter H. In any case, already with these two things, I have all the tools to state lemma. So this lemma will not have a nice, particularly nice shape, so but it's somewhat tailor-made in order to highlight this trick of subtracting a square from an arbitrary sum of squares in order to obtain certain properties. So it won't look too nice, but don't be scared. I will try to make it nicer right after. Okay, assume that there exists subring H. Oh, sorry. Subring such that first of all we want the fraction field of H to be the whole field. And secondly, we want all the sums of squares in F to be. I want them to be. I want to be able to write all the sums of squares in F as a square times an element which is 1 plus the sum of squares. So a sum of squares where one of the elements is 1. And at the same time, I want it to be in the Jacobson radical idea of H. If this happens, then the Pythagoras number of F is bounded by P star of H plus 1. So the proof go as follows. We take a sum of squares F. Let's take it 0 because it's treated as 0 is a sum of squares. So we apply, we exploit this hypothesis. So take C in F 0 and label F in the sums of squares plus 1, and at the same time in the Jacobson radical ideal, such that G is C squared times F. So, what we use of this condition is the following. So the fact that F is in the Jacobson radical will be used to obtain that 4F minus 1 is the unit. So that's why I give this characterization. The fact that F is 1 plus the sum of squares will be used to say that 4F minus 1 is belongs to 4 plus 4 times the sum of squares in F, right? F times 1. So of course, 4 times the sum of squares in the field are the sum of squares in the field. 4 minus 1 is 3. So 3 is the sum of squares, of course. So thanks to this condition, we get that 4 minus 1 is the sum of squares. Okay. And how do we exploit this element form F minus 1? Well, we subtract. We take our sum of squares G and we subtract C half squared. We collect our C half squared, and we obtain our special element 4F minus 1. Another fact is that this is a sum of squares, right? And also a unit in H. So by the definition of P star, 4F minus 1 will be a sum of P star H squares in F, right? Now we see how the square on both sides, and we get that G is a sum of P star plus 1 squares in F. So as you can see, I kind of built this lemma in order to show you the trick. But it's not really practical to like what is H, what is this P star in general. So let's try to make this a bit more applicable. Okay, so let's assume that there exist two positive integers and finite number of valuation rings, not necessarily discrete, just valuation rings of S with following properties. such that we want the level of the residue field of each these valuation rings to be 2 to the n. By this field, I mean the residue field. I. And second, we want this p star to be p star of the intersection of these valuation rings to be most to n. Then we find that the Pythagoras number of f is at most to the n. So you can imagine this theorem follows by the lemma. So the idea is simple. We just set just take H to be the intersection of these rings. Apply the lemma. So you need some valuation theory and standard algebra to show this hypothesis, but there is nothing too interesting. And then one concludes by the way. So, as you can see, this statement is already a bit more rigged, if you want, in the sense that if we have a local global principle for a field involving valuation rings, operations, and using this local global principle, we can identify certain valuation rings with residue level 2n. And we managed to prove this condition. Then we obtain a bound for the Pythagoras. So I could give you more technicalities to show you, to convince you that from a local global principle, one can obtain an upper bound for the P star, provided one can find certain valuation rings. But I think it's more interesting to trust me about this. It's technical, there's some valuation theory, it's really elementary somehow. And I would rather like to show you how to apply this result in a concrete situation. So let's take one of those fields that I mentioned before. So see application 1. Let's take the field this field here. So it's the function field of an elliptic curve over the base field of the form of our series, the real form of our series. So okay, now the result by Becker is gone, but if you remember in the example in this blackboard that's here before, I was saying that the Pythagoras number is almost 3. And this was shown by Becker in 2014, and how did they do? Well, they used a local global principle. From a paper of Koyutelen, Warimada, Suresh. And it's a local global principle for 3 and for 4 dimensional quadratic forms. So one, and you really use the local global principle for 3 and for 4 dimensional quadratic forms. Let me also remark, this is also a quite big result. So if you're familiar with it, you know, it involves some field patching and some serious techniques. So I would like to show you that with by using this. I don't know. I would like to show you that by using our theorem, one can prove this upper bound by significantly more elementary techniques, let's say. With the theorem, how do we do? Well, first, we want to apply the theorem with n and n equal to 1. And we will still need a local global ingredient, but this time the local global ingredient will be the result obtained by, will be hidden or be used in a result obtained by Becker, Green, Van Geel. No, sorry, by Becker and Van Geel in 2009. So by using only Milnor's exact sequence for the field. Okay, so an exact sequence for the rational function field, and our principle by Lam. I don't remember the year. So one can prove that there are only 2 classes of sums of squares, modulo sums of 2 squares. So maybe I didn't mention, but the sums of squares are a multiplicative subgroup of the field, the non-zero sums of squares. And so it is for all sums of 2 to the n squares, in particular for the sums of 2 squares. So by using elementary mathematics, the Milnor's exact sequence and the Milnor principle, which is a simple, relatively simple result for quadratic form theory, one obtains that this cardinality of this quotient group is bounded by 2, where 2 is 2 to the power of 2 to the 1, if we want, where 1 corresponds to the number of factors, non-real factors, let's say, factors of this kind would appear in such a. It's actually more general, but I would like to show it. So
This S2 is not a fluid.
yes, so the fact is that Okay, the sums of squares, the non-zero sums of squares are a group, right? Multiplicative group, of course. But the fact is that also the sums of 2n squares are a subgroup of F. This has to do with the fact that Pfister forms are multiplicative. If we want for the sums of 2 squares, there's actually the how is it called, the Diophantus quality. Okay, I don't remember it by heart. Sorry. It must be something like. Sorry?
Okay, the other one is AC minus B.
AC minus. Thank you. So this shows that this for n equal to 1, that this is closed under multiplicativity, and this simple trick shows that and this other trick shows that the inverse is also sum of 2 squares.
So we're actually using the fact that so if now this represented by Pfister form is a multiplicative group, the fact that the multiply Pfister form is
Yes. So, okay, it's true. I should have given a bit more details about this, but in any case, the fact is that if we apply this techniques to this field, we obtain an upper bound. So there are only up to 2 classes modulo sums of 2 squares. And yeah, so how can we conclude? Well, we need, as I said, I want to apply it with n and m equal to 1, meaning that there will be only one valuation ring, and it will be the valuation ring given by associated to the valuation B, where B is an extension of the Gauss extension of F, the Gauss extension to K R parameters T of X along X of the theoretic correlation. So let me just explain better. Our field is a quadratic extension of this field, right? So here we have the theoretic correlation. We take some form-of-our series. You take its order T and quotient and you get evaluation. We can extend it by setting by using the Gauss extension, meaning that for a polynomial like this, we set evaluation three. Take the minimum of let's even make this one. Okay. And now one can show that there exists an extension of the solution. Actually, in this case, there is only one, so it's actually a unique extension. But in any case, we can take evaluation V that extend this one, which is an extension of this. And then what happens? Well, we have Tx will have value 1. The residue field of this evaluation ring will be isomorphic to field. So in particular, it's easy to see that the level of this field is 2. And this also implies that the sum of two squares have value, have even value. In particular, Tx is not a sum of two squares. On the other hand, Tx is a sum of squares in F. This you can just use the equation of the elliptic curve. So if you set alpha equal to string, and you do some computations, you find that Tx is equal to 1 plus alpha squared. And I think something like this. So in particular, Tx will be a representative for the non-trivial class, right? So now you can see that these elements will have all odd values, because Tx is value 1 and this has given value. So when we intersect the units of O with the sums of squares, they are all in the sum of two squares, right? Which is what we were saying here. Our P star of O is at most 2, usually 1 if you want. And so we have this condition. We have that the level of the solution of the residue field of the solution is 2. So we have that the hypotheses of the theorem are satisfied for this solution, right? So by the theorem, we get the Pythagoras number of F is at most. We have recovered our result by using some of our more elementary techniques. Yeah, I wanted to give one more example, but I leave time for the questions.
Is the Pythagoras number determined by the cohomology? Right, by the cohomology?
There are relationships, so
Determined. If you know the cohomology, then you tell the Pythagoras number.
I don't think in general you need. I don't think in general, but in some cases there is strong relation. So the fact is that you can translate the, it's the Pythagoras number is given by a form can be translated into isotropicity of a specific quadratic form. So of the form this, right? So if this is is a power of 2, which happens in most of the fields we know, almost all the fields we know. Then this is a fixed circle, right? And a fixed neighbor, if you want. So you can translate this in terms of cohomology. So associate. Cohomology. It's not true that the Pythagoras number is always 2 to the n or 2 to the n plus 1. So for a long period, it was conjectured that all fields have Pythagoras number infinite, or a power of 2, or a power of 2 plus 1. But in the 1999 or something like that, they finally proved that there are fields of any Pythagoras number. So in those cases, I don't think you can relate the Pythagoras number to cohomology. Yes.
Just a simple example, simplest example, out of X. Can you make a formula?
Sorry?
Can you give me a formula?
For what?
If I'm giving you a polynomial over the R, and I'm telling you write it as a sum of squares. Is there like an algorithm?
Well, in R of X, yes. So,
Uh-huh.
so the fact is that okay, let's start with a polynomial. So if it's positive semi-definite, it will be a sum of squares, right? You can remove all. You can assume that it's positive definite actually up to squares, right? So polynomial, and we factor it into R of X, then it will be a product of linear terms times product of degree 2 terms, which will be sum of 2 squares. Yeah. So okay, this will have to go if you want them to be a sum of squares, and these are sum of 2 squares. So you not just need to factor it. But in general, for arbitrary fields, no. So I think one of the most important opera problem is whether this implication is true.
So it's not even, it's really not anything like a factor of 2.
It's not known. So if you remember, for the ones who were here a year ago, I was giving an example. This problem is open, but we computed this problem for a certain class of fields. We shown that this happens for a certain class of fields and gave it. Yes.
General perspective, what do we know about the case of quality? What can we say about
So in this case,
situation when it is achieved?
yeah, okay, for example, so, okay, this, as I was saying, is somehow you want to find a lower bound in some sense, right? And this is done in very different ways usually. I mean, with different techniques. So I can tell you in this case, this is true. So, and you can also see why. Because Tx is a sum of squares, but not a sum of 2 squares. X is a sum of squares, and Tx is not a sum. But yeah, I cannot tell you much from with these tools. Usually the techniques are quite different.
questions? Let's get ready. Take a 5-minute break and then 2:10.
So it should be like a one line or something. We just need to make that equation.
Yeah.
So it's about the square.
לא יודע, יש אנשים שמחלקים בווייטים.
זה עוקב אחריי?
Yeah, I think that the
זה כמו למחשב.
בוא תבקר, תלך לפרק.
אני עכשיו...
עושה קליק.